In this video, we'll learn how valence electrons are involved when atoms bond together to form molecules. The atoms are the building blocks, the molecules are the buildings. We'll represent molecules by drawing Lewis structures. When atoms bond together to form molecules, strong chemical forces are involved. We'll look at two types of interatomic forces, ionic bonds and covalent bonds. Chemical forces are involved when a stain stains a shirt. Chemical forces are also involved to remove a stain from a shirt. Here's one way to classify stains. Stains are enzymatic, oxidizable, greasy, or particulate stains. A greasy stain, that is an oil spill, stained the Gulf of Mexico in 2010. 5 common methods were used to clean up the stain. The oil spill stained marsh grass along a large part of the coastline along the Gulf of Mexico. The oil was spread beneath the surface of the Gulf of Mexico, on the surface, and above the surface. Dispersants were used to remove the oil from the water. This picture shows how chemical forces between the dispersant, oil, and water makes dispersant work. The structure of the molecules determines the chemical forces. Of the 4.9 million barrels of oil spilled, only about 25% was recovered, burned, or skimmed. The rest went into the environment. Another effect of the oil spill was on seafood. Scientists are developing new ways to clean up oil spills. Aerogels may be used in the future. Valence electrons are responsible for bonding, which tells about structure, shape, properties, and chemical forces. Let's review valence electrons. Stop the video and answer these questions. And the answers are: oxygen is a group 6 element. Is the valence electron configuration of oxygen? An energy level diagram tells us how many electrons are paired, how many are unpaired. So the Lewis dot symbol of oxygen should show 2 pairs of electrons and 2 unpaired electrons. Not 3 pairs, not 6 unpaired, and not 2 triplets. Atoms in a stable molecule will follow the octet rule, in which there's 8 electrons in a completely filled shell. Stop the video and answer these questions about oxygen. And the answers are: oxygen atom, which has 6 valence electrons, gains 2 electrons to get a completely filled shell. The oxide ion has a -2 charge. So atoms will gain or lose electrons so their outermost shell is completely filled. This results in a stable, low energy state. So let's see how these ideas are involved when atoms bond together to make a compound. Stop the video and answer these 2 questions. And the answer in each blank is: sodium chloride is an ionic compound. An ionic bond forms between the sodium ion and chloride ion. An ionic bond forms when sodium transfers its valence electron to chlorine. Sodium ion and chloride ion have completely filled shells. The electrostatic attraction between the plus charge and minus charge is the ionic bond. Do not use a line to show an ionic bond. For hydrogen chloride, H has 1 valence electron, chlorine has 7. A covalent bond forms when 1 unpaired electron from hydrogen combines with 1 unpaired electron from chlorine. That bonding pair of electrons is shared between the H and Cl. Chlorine now has 8 electrons around it, which gives it a completely filled shell. That's the octet rule. Hydrogen has 2 electrons around it, which gives it a completely filled shell, the 1s atomic orbital. That's the duet rule for hydrogen. A single line represents a single covalent bond, which consists of a bonding pair. So you can use a line to represent a covalent bond instead of 2 dots for the bonding pair. So again, lines for covalent bonds, not for ionic bonds. The structures of diatomic hydrogen and methane gas are also shown. Okay, so stop the video and review these rules for drawing a Lewis structure of a molecule. These general bonding rules apply for most structures, so go back to the previous slide and you'll see that these bonding rules apply to those 3 compounds. This country has a lot of natural gas, which consists mainly of methane. We burn methane as a fuel, so stop the video and draw the Lewis structure of each reactant and product for the methane combustion reaction. Here's the methane combustion reaction. Here are the Lewis structures of methane and water. For oxygen, A single covalent bond gives each oxygen 7 electrons around it, not the 8 for the octet rule. With a double bond, each oxygen fits the octet rule. And for CO2, with a single bond, the C and the O's do not fit the octet rule. With a double bond, it does. We learned earlier that all chemical reactions involve energy. That energy is stored in those bonds. Nitrogen triiodide is a compound that decomposes explosively with the touch of a feather. Stop the video and answer these questions. And the answers to the Lewis structures are, for the other questions, this reaction is exothermic. Ni3 is an explosive, which means that it has weak bonds. The decomposition reaction is exothermic, and the reaction is very fast. Scientists are developing environmentally friendlier and more powerful explosives. We looked at the Lewis structures of Ni3, I2, and N2 earlier. A polar bond has a positive pole and a negative pole, just like a magnet. Each atom has a different ability to attract the electrons toward itself. That's called electronegativity. So when two different atoms are bonded to each other, that's going to be a polar bond. The Ni bond is weak. It doesn't take much energy, such as the touch of a feather, to break that bond. So Ni3 is unstable because of those weak Ni bonds. In N2, the nitrogen-nitrogen triple bond is very strong and releases a lot of energy when it forms. So the unstable high-energy Ni3 reactants form stable, low-energy products. That makes the reaction exothermic, and because the reaction is fast, Ni3 is an explosive. Hydrocarbons are organic compounds that often are used as fuels. So stop the video and draw the Lewis structure of ethane, ethylene, and acetylene. Here are the answers. Stop the video again and answer these questions. And the answers are, in real life, atoms are not connected together by lines like shown in our Lewis structures. The distance between atoms tells us whether it's a single bond, double bond, or triple bond. In a triple bond, the atoms are close together. In a single bond, they're farther apart. So a carbon-carbon single bond requires the least energy to break. A carbon-carbon triple bond requires the most energy to break and releases the most energy when formed. We looked at polyatomic ions earlier. We can draw the Lewis structure of a polyatomic ion. For anions, add electrons that corresponds to the charge. For cations, subtract electrons. Stop the video and review the Lewis structure of the hydroxide ion. Note that oxygen satisfies the octet rule and hydrogen the duet rule. Stop the video again and draw the Lewis structure of the hydronium ion. So here's the answer, and here's the structure. Beverages are carbonated by bubbling carbon dioxide in the beverage. Carbonic acid forms. Stop the video and draw the Lewis structure of carbonic acid and bicarbonate ion. Here are the answers. As molecules get bigger, there's different ways to bond or connect the atoms together. Isomers are two compounds that have the same chemical formula but different bonding. Each isomer usually has different properties. So stop the video and draw the two isomers of C2H6O. And here are the answers. The one on the left is ethanol, an alcohol which us humans can drink in small quantities without getting too sick. The one on the right is an ether, a common organic solvent. Note that these molecules and the molecules we looked at earlier fit the general bonding rules: 4 bonds to carbon, 3 bonds to nitrogen, 2 bonds to oxygen, and 1 bond to hydrogen. Ions, on the other hand, may not fit those bonding rules.